Hello, welcome to the channel of Namagiri Academy. Mm, In the previous lecture, while studying the multiple integration, we saw how to integrate over the regions that are not rectangular. So we are studying double integration in particular rather than saying multiple integration. So now we shall go one step ahead, and in this video we shall see how to change the order of integration. This is very important because sometimes changing the order of integration um, simplifies computation. So we shall see how to change the what it means by changing the order of integration. We have actually discussed it in the previous lecture. So in double integration, we actually integrate uh, using the idea of iterated integration. That is, first we integrate integrate with respect to one of the variables. That is, if suppose we are integrating with respect to x and y, then we integrate with respect to x first and then y, or sometimes we integrate with respect to y first and then with respect to x. This is called as iterated integration. And suppose if we are given an integral, a double integral, uh, which is written initially in such a way that we are supposed to integrate it first with respect to x and then with respect to y, then converting it into the integral wherein we are required to integrate it with respect to y first and then with respect to x, then we call it as the changing the order of the integration. We shall see some examples how to change the order, and also the uses of changing the order by seeing how it simplifies sometimes the calculations. All right. So in the previous examples that we saw, the region of integration was given to us, and therefore it was easier for us to um, change the order of the integration. Now let us see what if we are not explicitly given the region of integration. In such cases, we shall have to draw the region of integration by ourselves. So let us take one example. Change. Let me write it in this way. Change the order of the following integral. So this is I'm not writing the function, let it be f of x y, because now that we are only changing the order of the integral, what really matters is the region and the interplay between the limits of the integrals. So this function actually has nothing to do, has no role to play here. Here I would write you see here that here we are first um, integrating with respect to x and then with respect to y, and the limits of integration of f with respect to x are expressed in terms of the functions of y. So when we actually integrate f, we shall get this expression in terms of x, and then we shall substitute the limits, and then we shall integrate with respect to y. Alright, so before we can change the order of the integral, let us draw the region that these limits represent. Alright, so let this be these be coordinate axes x and y. Now x equal to y square, so x begins from y square, and it runs from y square to square root of y. So x being x equal to y square, the graph of x equal to y square is this in the first quadrant. In fact, it is x equal to y square can be drawn like this, the total, I mean the complete graph. Okay, fine. And the graph of x equal to square root of y is this. The total graph is like this. So x equal to square root of y is nothing but y equal to x square. So it is this. So to say, the complete graph is this. Okay, so fine. So now what we want is, we want for every fixed y, we want x to run from square root of from y square to square root of y. Remember that we want to go in the positive direction. So x will run from the smaller value to greater value. So here y square is this is x equal to y square, and this is x equal to square root of y, which can alternatively be written as y equal to x square. Now these two parts of these two graphs become irrelevant in this case, because the region that we want to consider becomes bounded by these two curves for every y. Now here we are considering y ranging from 0 to 1. Observe that here this is 0, 0, and this is the point where these two curves meet, and the coordinates of this point these are 1, 1. So it is actually exactly y equal to 1, and this is 0. So y is running from 0 to 1 here, as you can see, and for every such y that lies between 0 and 1, x is varying from y square to square root of y, and in this way we get our region. So this part and this part become irrelevant. Let us not bother about it. So this is our region, and we are trying to integrate f in this region. Now what we want to do is, we want to change the order of this integral. So now we want to view the same region in a different way, in which we shall vary x independently. That means here, as you can see, x also varies from 0 to 1, and then accordingly we shall see for every value of x, what are the values of y between which y varies, right? So for that, let us rewrite these equations. So this first equation is x equal to y square can be written as y equal to square root of x, and this is x equal to square root of y can be written as y equal to x square. The same region, the same curves, but now since we want to express y in terms of x, we are rewriting the equations. Okay, so now again here this is 0 and 1, this point is 1 comma 1, here this point is also 1 over here, y equal to it is 0 comma 1, this is 1 comma 0. Okay, so now here for every y we varied x from y square to square root of y. Now here for every what we shall do is we shall vary x from 0 to 1, and for every x here between 0 and 1, y varies from this point to this point, because we want to cover this area, this region. Okay, so how can we write this? X is varying between 0 and 1, and what are the boundaries between which y varies? Sorry, not 0. Remember that we have to go from smaller value to greater value, okay, in the positive direction always. So x square to square root of x, this is the lower limit of y for every x. So x square to square root of x, which is the upper value, which is bounded above by this curve y equal to square root of x. So y varies from x square to square root of x, and that covers the whole region. So we can write this integral equivalently as f of xy. Now first we shall be integrating with respect to y. The limits of integration are x square and square root of x, and then we shall integrate with respect to x, wherein the limits of integration with respect to x are 0 and 1. So now we have changed the order of integration. Observe here. Okay, here first we integrated with respect to x, and then with respect to y. Here exactly opposite is happening, first y and then x. This is called as the order, changing the order of the integration, and for that we have drawn the region and observed how limits of integration behave. We have to give a careful look to the limits of integration of x and y, and we have to change them accordingly when we change the order of integration. So this was an example. This was a relatively simple example. Let us take a little complicated example, so to say. So again I will not write the question, change the order of integration. So it is 0 to a. A is some arbitrary constant. We shall assume that it's a positive constant for our for the sake of simplicity. Y varies from x over 4 to 3a minus x. This is our integral and we want to change the order of the integration. So again here begin by drawing diagram. Let us draw this diagram. So first y varies from x over 4 to 3a minus x. So suppose y equal to 3a minus x can be equivalently written as x plus y equal to 3a. So it is a line passing through 0 comma 3a and 3a comma 0. So let this be a line of this sort. Okay, this is the y-axis. Okay, fine. And y equal to x over 4 is the line which is passing through the origin and having slope equal to 1 over 4. So something like this we can roughly draw it in this way. So these two lines intersect at this point. We want y to vary from x over 4 and it is bounded above by this line 3a minus x. So it is this region between which y is allowed to vary. But is this the triangle over which we are integrating? We are not yet sure because we haven't yet given a look at the range of x. Okay, so let us first find out the point of intersection of these two lines. Here the two lines intersect and here we have y, this line is y equal to x over 4. So since the y coordinate of these two lines is same, we can write x equal to 4 x over 4 equal to 3a minus x, which means after solving for x we shall get 5x over 4 equal to 3a, and then this will mean x equal to 12a divided by 5. So this point is 12, the x coordinate is 12a over 5. And what is the y coordinate? It lies on the line x over 4. So suppose if we substitute 12a over 5 in this, then it gives us 3a over 5. So this is the point. All right, good. Now what is the um, what are the limits between which x varies 0 and a? This observe that this 12 a over 5 is larger than a. In fact, it is larger than 2 times a. It is 2.4 a. Okay, so suppose if this is 2.4 over a, so this is a, this is 2a, and this is 2.4a, something like this. The situation is something like this. So a is here, and we are allowed to vary x only from 0 to a. Now for every x that lies between 0 and a, y varies from x over 4, that is this line is x over 4, which is the lower limit for y, to 3a minus x, which is this upper line, upper bound on y. So actually it is this region, between the region, the desired region. Okay, this is of no use, or this is something that we should not take into account. Okay, so it is this region, this trapezium, as you can call it. Alright, now we want to change the order of integration, and this is a little apparently a challenging task, because suppose we are sure that here that y varies from 0 to 3a, because we have already seen that this is the line which connects 0 comma 3a and 3a comma 0. But what is the value of x that between which two values does x vary for every y? That is what we want to decide, because here in this case x varies from 0 to the point that lies on this line. Here in this case x varies from 0 to a. This is the line x equal to a. Here in this case, in this part, x lies from 0 to the point on this line, and so therefore you can clearly see that there are 3 different cases over here. So we shall have to divide this whole integral, this whole we shall divide this trapezium into 3 regions, and then we shall compute the integral. So now it is needless to say, I don't remember whether I have told you this or not, but the integral of a function over a region can be split into several regions that are contained inside that region. So you can so we can, in this case, we can split this region R into this region R1, this triangle R1, sorry, this rectangle R2, and this triangle R3. So let me write this as R3, this as R2, and this as R1. Now, okay, good. Let us look at the R1. what are the fine. So how will should we decide the the boundaries of x and y for R1? Let us write this is the equation of line x over 4. So x can be written as 4y in this case. Let me repeat, this line is y equal to x over 4, which is the same as x equal to 4y. And what is this? Point. Okay. So to compute the limits of the integral for this triangle R1, observe that this is the x coordinate of this point is A, and it lies on line y equal to x over 4. So the y coordinate will be A over 4. Alright, so this is the y coordinate, the height from the x axis. So this is A over 4. Alright, so for this triangle, y varies from 0 to A over 4, and okay, for R1, so we are now considering R1, y varies from 0 to A over 4, and x varies for every y between 0 and A over 4. X varies from 0 to this point on this line, which is the line x equal to 4y. Remember that now we have to express x in terms of y. So x is now varying from 0 to 4y. Okay, good. Alright, so now this is about R1. How about R2? R2 is clearly a rectangle, and we already know how to compute the integrals over rectangles. Here this this point also has x coordinate equal to A, because this is line A, x equal to A, and this point lies on the line 3y equal to 3a minus x. So what will be the y coordinate of this point? It will be 3a minus a. Okay, by substituting a for x, so 3a minus a, so y will be 3a minus a, which is 2 times a. So this is the y coordinate is 2a, meaning that this is 2 times a. So now what are the ranges of x and y for this rectangle? Y varies from a over 4 to 2a, sorry, not 0, I'm sorry, a over 4 to 2a, and x varies from 0 to a. Here the value of x is independent of y because it's a rectangle. And the final thing is R3. For R3 again we shall have to express x in terms of y is equal to 3a minus x is the equation of this line, which we shall write as x equal to 3a minus y. Alright, now here we have y varying for this rectangle R3. Now this is not rectangle, sorry, triangle region, I mean this region R3, y varies from 2a to 3a. And what does x vary between it? For every y from 2a to 3a, it will vary from 0 to this point, and this point lies on the line x equal to 3a minus y. So 0 x less than or equal to 3a minus y. So these are the limits of the integration. So now what shall we try to do? This whole integral can be split into the integrals over these three regions. When we change the order, we shall have to split it into these three regions. Okay, so fine. So integral over f of x y dy dx x over 4 3a minus x 0 to a, that is the original integral given, is equal to, now integral of the same function first over the region R1. But what is the region R1? Now we shall be changing the order of the integration. First we shall integrate with respect to x. So for region R1, the limits of x are 0, 4y, and y will vary from 0 to a over 4 dx dy. This is the integral over the first region. Now integral over the second region, f of x comma y, this f doesn't change, dx dy, x from 0 to a, and y will vary from a over 4 to 2 times a. Here these limits plus f of xy dx dy, x will vary from 0 to 3a minus y, and y will vary from 2a to 3a. So this is how we have written the integral after changing the order. So so when we change the order, we may have to split the region into more than one regions. This is one demonstration of that. Alright, so this may give rise to a question that why are we doing it because it apparently looks difficult. I mean, it looks like it is becoming more complicated since we have to split one region into more than one regions. But very often computing rather it is probable that the integral gets split into more than one regions, but integrating function with respect to one variable first and then the other variable becomes easier, and therefore sometimes we um, choose to change the order of the integration. So let's take one example to demonstrate this fact. um, Consider that I would write compute um, this is one example. Now here observe that first we are integrating with respect to y, and after substituting the limits in terms of x, we shall integrate with respect to x. Now considering this function f of xy as a function of y, it is really very difficult to integrate. You can certainly give your hand and try your hand on that, and you may come up with answer. It's not that you cannot integrate it, but if we change the order of the integral, then it becomes much easier. But in order to do that, first we shall have to decide the limits of appropriate limits of integration. So first let's draw the region that will help us to determine the limits of integration. Observe that y is varying from 0 to 1, so something like this, from 0 x is varying from 0 to 1, so from here to here, something like this, and y varies from x to 1. So if we draw the line y equal to x, that exactly bisects these two, and this first quadrant, y equal to x. Okay, so suppose this is x equal to 1, then this is y equal to 1. So x varies from 0 to 1 and y varies from x to 1. So it is this region, so it is this triangle basically that we are integrating over. I hope you understand. Now how should we change the order of the integral? Give it a thought. Now we want to first fix y, and then see for every y between each two values x varies. So y will vary from 0 to 1, and for every y x will vary from 0 to y. Okay, this is the line x equal to y. Okay. So this can be written as y will vary from 0 to 1, x is varying from 0. Remember that don't write this as 0 to x. The y and x are equal on this line, so you can be tempted to write 0 to x but we don't want that because we want to express x as a function of y. Always when we are writing, we are integrating with respect to x, the limit should be in terms of y, and when we are integrating with respect to y, the limit should be in terms of x. The function remains unchanged, but now the order changes. Alright, so now this is the region looked when we look at it differently. Now see that suddenly it looks simple, because now since we are differentiating with respect to x first, this y over 1 over y square becomes constant. It may be taken outside the integral sign, this first inner integral sign. Okay, so we can write this as, so I have not this is, in fact I would write equal. I have explained everything by changing the order of the integral, etc. I haven't written it anywhere, but you understand it. Alright, so 0 to 1, inside I would write y over 1 plus y square integral 0 to y. It is as if we are taking a constant outside the integral sign. Dx 1 plus xy square dy. Now this is 0 to 1. Now this is of the form a plus bx. Now here again y is constant, so 1 is a constant, of course, so it is like 1, so a plus bx the square. So we can use here the formula for integral of ax plus b to the power n, where n here is negative 2, and that will give us y over 1 plus y square over y. Now here this is the integral 1 plus xy the power minus 1 divided by minus 1. This is the integral. This constant comes in the denominator. And the limits of integration are 0 to y. This is the inner integral. Outer integral still remains to be computed. Equal to, okay, this is continued here. Zero to 1 y 1 over y square So this will be uh, uh, this y gets cancelled here and here, so we don't have to write this y. Okay, so 1 over y square. Okay, so some simplification, and this negative sign can get absorbed uh, in here, so we can change these limits at the expense of this negative sign. So we can write this as 1 over 1 plus xy 0 y dy. Now this is we are now substituting for x, because we have integrated with respect to x. So when we substitute x equal to 0, we get 1 here, 1 over 1 plus 0 minus 1 over 1 plus y square dy. Okay, so now this is 1 plus y square minus 1, so it becomes y square over 1 plus y square dy. Now it becomes just a function in y square which you want to compute, and I will just leave it to you as an exercise to solve it. I think you can solve it using substitution. You can use substitution. You can substitute y equal to probably tan of theta or something like that, and you can get it solved. So, but the reason why we did it is for showing that if we change the order of integration, the process of integration becomes much simpler. Had we tried integrating with respect to y initially, it might have become very messy and extremely difficult to solve. So by changing the order of the integral, changing the order of the variables, we can easily solve some of the problems. So whenever you are whenever you see an integral, double integral or triple integral, especially now since we are dealing with double integral, check look at the function that you are trying to integrate. When you see, if you see that integrating with respect to a specific variable is easier than the other variable, then always integrate with respect to that certain variable first, and then think of integrating with respect to the other second variable. If for that you need to change the order of the variables, then please do that. Change the order of the variables, integrate with respect to the variable with respect to which it is easier to integrate, and then integrate with respect to the second variable. That is the moral of this story. Okay, so we shall stop here and we shall continue in the next lecture.